Hi, my name is Colin McAlvain,
Hi, my name is Vincent Hu, and I also go by Shelley.
and we are doing a paper on thermoelectric synthetic skin for powering implantable biomedical devices. So the idea behind our paper is biomedical devices require long-term sustainable power sources, and currently we mostly use batteries inside the human body. It's fairly invasive to get batteries inside of a lot of these devices, and we were wondering if it was possible to use human body heat in order to power these devices externally and using a source of power that we already have. In this paper, you'll see how we optimized open circuit voltage and power output using this technology. And we used ordinary differential equations, partial differential equations, and steady state heat conduction models in order to simulate that this would work. We have a couple of key concepts here that we used. The Seebeck effect was particularly important as it's the thing that allowed us to create a voltage across our temperature differential. And we'll get into the thermoelectric voltage generation and the current and power estimations as well. Motivation for this problem. Like I said a moment ago, implanted biomedical devices rely on internal power sources that are often invasive to install and require multiple surgical procedures. The idea behind that statement is if you need a battery inside of a pacemaker, you have to open up somebody's chest in order to get that battery inside of there. And that's obviously not great for the patient. But they need the pacemaker. The technologies are important. So we wanted to see whether or not we could find a power source that was easier or less invasive and more natural with the human body. Um, okay, so the three principal effects we're using here are the Seebeck effect, the Peltier effect, and the Thomson effect. The Seebeck effect is when a voltage is generated when there's a temperature difference across two dissimilar conductors. The Peltier effect is when heat is absorbed or released at the junction of two different materials. And the Thomson effect is when heat is continuously absorbed or released along a single conductor. These three effects are used in order to generate a voltage for our project. Uh, Essentially, since this is a synthetic skin, we have several layers that we used in order to achieve our thermoelectric generation. The PET substrate is the portion of our synthetic skin that actually adheres to the body. This is going to be a primary heat conductor for body heat. Then we have the SHC and SHI composite layers, which are used to transfer the heat to the TE legs and insulate the temperature so that we have a consistent temperature. We're not losing excess heat inside of the material. The TE legs are thermoelectric materials to generate voltage from heat flow, and the electrodes collect and transmit the generated current. So these five layers, allow our synthetic skin to theoretically generate energy.
All right, just like what Colleen have mentioned, we have this main multi-layer synthetic skin setup for our simulation. At the first, very bottom layer, we have our core body temperature, which is the main boundary conditions and where the heat mainly comes from. And the second layer is the substrate that adhere to our human skin. And on top of that, we have two components, that is the soft heat conductor and soft heat insulator. And the majority amount of heat will comes through the soft heat conductor and reach the top layer, the thermoelectric leg that is made of aluminum nitride. That creates a temperature difference at the between the hot end and the cold end. And the hot end lays on top of the SHC, and the cold end lays on top of the SHI. And due to the temperature difference, we have open circuit voltage induced in this TE lag, which in turn produce power output when there's a electrical load connected in to the circuit. So the main goal of this simulation here is to figure out what is the optimized open circuit voltage. Um, and the as you can see on the left-hand side, we have this two equations. The open circuit voltage, VOC, is the product of Seebeck coefficient of the thermoelectric lag and the number of thermoelectric legs that we connect in series. And lastly, the temperature drop between the hot end and the cold end of each thermoelectric leg. And the temperature drop is very definitively calculated by the difference of hot end temperature and the cold end temperature. So as I said before, the main goal is to figure out the optimized open circuit voltage, which in turn requires a maximized temperature difference, delta T. Um, Next slide, please. So in order to further simplify this modeling system and also to come up with a um, computationally effective algorithm that calculates the optimized parameters, for example, the thickness of the substrates layer and the SHC, SHI layer, and lastly, the TE lag layer, and come up with a maximized VOC. We made the following assumptions. First of all, we assume that there's no time-dependent changes in temperature, which namely is the steady state assumption. So that all the heat equations that we use in this simulation does not have a time component. Secondly, we have this simplified 1D geometry for the initial analysis to come up with the hot end and cold end temperatures. Um, Thirdly, we have multiple layers and several materials in this material stack. So for each of the layers, we assume a consistent thermal conductivity, but across layers, we do deal with the a map of various thermal conductivities for the system-wide simulation. Um, and the fourth assumption that we made is we assume there is negligible radiation compared to the magnitude of heat conduction as the main heat transfer means in the system. The next assumption that we made is ideal contact interfaces, which means the matching between between every two layers are 100%. There are not going to be air gaps and heat loss through the heat transfer through the interfaces. And lastly, we have this assumption that says no internal heat generation. So the only heat source in this system comes from our human body, and none of the layers inside or above the human body layer generates any additional heat. Next slide, please. All right. In order to carry on our simulation and calculate the hot end and the cold end temperature, we have segmented the system into two parts. The left-hand side segment is what we call hot end, and the right-hand side is the cold end. And in each of the segment, we assume a steady state 1D heat conduction. So as you can see on the left-hand side, there are two equations, and the top equation is the steady state 1D heat conduction equation, which is composed of the product of thermal conductivity of the material in that layer and the second derivative of temperature with respect to Z. And because we assumed the steady state condition, so there is no time component on the right-hand side, which is equate to zero, um, which allows us to cancel out the thermal conductivity components that gives us this very simplified 1D heat equation. Uh, D, the second derivative of T with respect to Z equal to zero. That leads to a general solution that is T of Z equal to A plus BZ. And A and B in this equation are both constants. In addition to these linear equations, we also, next slide, please. We also have those governing equations that describes the boundary conditions to help us solve this linear system. The first one that we use here is the continuity of heat flux, which is dictated by this equation that is K sub I times D sub I over dz equal to D sub I plus 1 times dt sub I plus 1 over dz. And basically what that equation says is on either side of any interface between two layers, um, the the heat flux on one side of the interface is equal to the heat flux on the other side of the interface. That facilitate this continuity of heat flux assumption. The next boundary conditions that we use is continuity of temperature, which is simply that the temperature on one side of the interface is equal to the temperature of the other side of a material interface. And those two boundary conditions also allows us to have enough parameters to set up uh, the linear systems in the next slide. Here we have this 6 by 6 linear systems, which is composed of boundary conditions and those general solutions that is dictated by the continuity of temperature and continuity of heat flux. And using that linear system, we can have infinite number of solutions. Therefore, we wrote a Python project to optimize the material thickness to maximize T hot because by the nature of the linear system, we can have infinite number of T hot values. So we picked the best one for our system using a Python optimization algorithm. All right, so the next step that we went through is to figure out the cold end temperature. Um, in order to figure out the cold end temperature, we also made a list of assumptions to simplify the simulation and improve the computative um, efficiency. And the first one we made is the PET layer is insulated at the upper surface because it is directly interfaced with the SHI, which is the insulator layer. And that SHI layer has much higher or um, actually much lower thermal conductivity compared to the substrate. Therefore, we can assume a perfect insulation on the top surface of the PET, which means in steady state, we will have um, the body temperature on both the bottom surface that is directly in contact with our human body and the top surface of the PET likewise. The second assumption that we made is there is no lateral heat conduction between the SHC and SHI to simplify the system. The third assumption that we made is the heat flux at the SHI TE interface has only Z component, and this is justified by the fact that the width of the H SHC is way smaller than the width of the TE lag. Therefore, in any localized area in that TE lag that is reasonably far away from the hot end, we will see a very consistent or near to zero temperature gradient across the z-axis. Therefore, that gives us the justification to assume a z-only heat flux at the interface between the SHI and TE. And the main boundary conditions we assume for this cold and temperature calculation is the conductive heat loss at the top surface of the TE lag because of the airflow. And that equation, that heat transfer behavior is dictated by the equation on the left, the bottom left corner. Next slide, please. So with all the boundary conditions and the 1D simplifications, we come up with this 2 by 2 linear systems that's on the top left corner, combined with the 6 by 6 linear systems that dictates the behaviors of heat transfer in the hot end. We were able to come up with a algorithm that optimized not only the T hot, but most importantly, the delta T to maximize the open circuit voltage. Next slide, please. So with that two linear systems and the algorithm that we came up with, we reached at this list of optimized parameters, namely the thickness of the PET layer, the thickness of the SHC layer, the thickness of the TE layer. As you can see that because of the bounds that we set for those layers to minimize the thickness of the synthetic skin to facilitate the comfort of use. We have most of the thicknesses in the scales of tens of micrometers. Um, and the second half of the optimized parameters are the T hot, which is at 309.84 Kelvin. The cold end temperature is 301.15 Kelvin, which leads to this delta T that is the goal of the simulation, and we reached at 8.69 Kelvin. Next slide, please. So with the cold and hot and temperature and the delta T, we now have the in and also the thickness of each material layers. Now we have the enough parameters to simulate the thermal distribution in the TE lag. And in order to um, model for the temperature distribution in that component effectively, we made the following simplifications um, to simplify the equation that you see on the bottom left hand side, which dictates the thermoelectric behavior of the T lag. And the first simplification that we made is weak due to the weak temperature dependency of the TE lag seatback coefficient, we can basically remove the the third term of this equation that you see. And due to this no spatial variations of seatback coefficient, that also justify the removal of the third term of this equation. And lastly, because we are assuming steady state and open circuit conditions, the current density is effectively zero. which allow us to remove the second term of this equation, so that we are only left with this very simplified 2D heat conduction equation that is equal to zero. And with that 2D heat conduction equation, we also need the boundary conditions to complete to complete the simulation setup. On the bottom and the right boundary, we assume the Dirichlet condition, that is the cold end temperature. And on the left-hand side, we also assume a Dirichlet condition that is the hot end temperature. And on the top end, we assume a Robin condition that is yielded by this convective heat loss equation that we have mentioned before. Next slide, please. And with all that heat conduction equations and boundary conditions, we were able to simulate the temperature distribution in the 2D manner that is in the domain of the TE lag. And from this plot on the right-hand side, we can see that our simulation actually confirms a steady temperature drop from 309 Kelvin to 293 Kelvin across the multi-layer skin structure. And furthermore, the lateral heterogeneity from the SHC and SHI domains causes the localized differences in temperature distribution along the x-axis. As you can see, the pocket of yellow spot on the top left corner, that is yielded by what's the heat that's conducted from the small SHC component that is on the layer below the TE leg. Next slide, please. Um, from the simulation above and the linear equations that we have set up, we were able to plot this relationship between the delta T and the ambient temperature to test our systems under extreme temperature conditions. As you can see here, the colder environments at 0 degrees C increases the delta T and sharpen the thermal gradients, which allows us to achieve a 19.04 Kelvin temperature difference. Towards the right end of the plot, at 40 degrees C ambient temperature, we see a effectively zero Kelvin temperature difference. And that causes the heat inversion when the ambient temperature is higher than the body temperature. Next slide, please. A very similar negative correlation between the open circuit voltage and the ambient temperature can be seen in this plot as well. Our open circuit voltage reaches 179.1 millivolt at 0 degree C ambient temperature and drops to 0.54 millivolt at 40 degrees C due to the reduced delta T.
So what does all this mean as far as our thermoelectric synthetic skin is involved? Performance and practicality. The colder the environment you're in, the better this is going to work. So as you saw in the previous slides, uh, we're trying to maximize our delta T in order to get the most performance we can out of these devices. In fact, if the ambient temperature gets to be greater than body temperature, as it does as the closer to the equator we get, you actually see negative performance or no performance inside of the system. So this system works best when there's a large difference between the outside temperature and your body temperature. This limits the practicality in some senses, but at the same time, most people are in air-conditioned environments nowadays. So we have some sort of steady state built-in expectation as far as uh, consistent output of the device goes. So because we live in the correct environments, we or because we create the correct environments, we can expect this technology to work the majority of the time, which also brings up our need for some sort of power storage source so that when we're in effective climates, we can store the power that we have. Environmental and biological. Oh, because the pet or the synthetic skin is so small and made of certain synthetic materials that are discussed in some of the papers that we provided as as outside justifications. We can see that the skin is resilient in normal everyday life. And the mathematical modeling we used a lot from this class. Um, Obviously, since we're dealing with electricity, there's a lot of imagine or complex numbers involved, which involved the use of Laplace equations, particularly in the 2D and 3D regions of steady state heat conduction. We used Poisson's equations with the TE legs, internal heat generation, separation of variables, ordinary differential equations used in 1D models for the pets, boundary condition formulas in order to effectively model temperature, flux continuity, and convection heat loss, piecewise definitions of material properties, current density modelings, and energy conservation and nonlinear PDEs. The conclusion for our project is we believe that the feasibility of this technology is proven using the mathematical models that we've presented to you today. Um, the key mathematical principles that we were able to use were Laplace and Poisson's equations, separations of variables, and boundary conditions and continuity equations. We think that this project will have a positive impact on the medical field, um, mostly because it does provide a source of energy that you carry around with you everywhere, which is your body. Future work that would be need to be done in order to make this technology more feasible. We need to see what kind of cost it would require to make and distribute this, especially if we're going to create some sort of synthetic skin that is comfortable for somebody to wear at all times and make sure that it is safe for people to wear. We want to make sure that there's not so much of a current or a unforeseen defect in the material that it might cause burns or electrical issues of any kind. Um, and then, of course, device longevity. It would need to be a product that could last as long as a traditional battery might in any of these implanted devices. Here are a list of references we used in order to come up with the conclusions that we came here today. And if you have any questions, we welcome questions and feedback inside of the discussion section, and we will do our best to respond thoughtfully and thoroughly. Okay, yeah. Oh, I have to find the